Good evening.
Okay.
Welcome to Exoplanets. Dr. Aaron Coyner, NASA JPL Solar System Ambassador, will now speak on exoplanets. Dr. Coyner.
All right. Thank you, Drea. Well, welcome everybody, and welcome to, we're going to take an hour to get about as far away from the present situation as humanly possible, while still remaining at least somewhat scientific. Today's talk is exoplanets. I subtitle it Worlds Beyond because we're basically looking for planets around other stars, and we're doing so in a number of different ways with a number of different satellites and through a number of different mechanisms. And if we let PowerPoint actually behave, sometimes it does and sometimes it doesn't. There we go. All right, so first of all, what exactly is an exoplanet other than a good escape mechanism? Exoplanets, defined as any planet discovered outside of the heliosphere, which is anything outside of our solar system. Candidates are many different sizes, many different compositions, many different types of systems. And to date, between Kepler, TESS, and other methods, and I literally checked these numbers yesterday. They may have changed again because they do tend to do that. But as of yesterday, or as of 2 days ago when I recorded this number, we have 4,292 confirmed exoplanets, 5,587 candidates, and a total of 3,185 different planetary systems of different sizes, shapes, and general craziness. And that was as of 2 days ago. I fully expect if I were to give this talk again in January that number would be bumped up by a couple hundred, just because that seems to be the track that things are going now that we have the resolution to be able to pick some of these things up. So exoplanets are far more prevalent than we had initially thought. When I was in school, we often thought of our planetary system as the 9 planets that we do have, the 9 planets that we have, the asteroid belt, and then the Kuiper belt objects, which is now due to the International Astronomical Union deciding to do things that not everyone necessarily agrees with, is the 8 major planets, and then there's 5 dwarf planets, including Pluto. So some of us argue Pluto is still a planet. I'm very much in that camp, but officially it's listed as a dwarf planet. Although, why do we discriminate on these things? If we include all the planets and the dwarf planets in our solar system, we're looking at like 15 or 16 now, because they're finding more dwarf planets every year. And then we have, beyond our solar system, we're looking at exoplanets. These are planets that range from planets the size of Jupiter that orbit inside the orbit of Mercury compared to their star. We've got planets that are larger than Jupiter that are really, really close in. We've got Earth-like planets. We've got Neptune-like planets. We've got what are called super-Earths that are like Earth but slightly bigger. We've got any number of different classifications. And I'm not going to take full credit for this because there are a few slides in this talk that are actually taken from a presentation by Dr. Joshua Schleider from I believe MIT, and was working on the TESS project. You'll see some of his other credit slides here in a little while, and he was talking about what to do with why do we want to study exoplanets? Well, studying exoplanets and finding planets outside of our own solar system lets us study planet formation and how we believe planets form and evolve from sort of disks of gas and dust to clumping together into giant forms of rocky and or gaseous and or icy matter? And then how do we figure out what the compositions of the atmosphere is, and how do we have system evolution when they start to play pool with each other and knock each other out of orbit? Do they get sucked into the star and burnt up? Do they get flung out into outer space and never seen again until we get to stable orbits, or what exactly happens? The second question we always have is, okay, so we can find planets elsewhere. What do they look like compared to the planets we already know? And what can we say about the stars that have planets? And how frequent is it for a star to have planets? And what do we know about the distribution of what these planets actually look like? And these can tell us more about sort of the evolution of the universe and the evolution of various solar systems. I'm not going to talk a whole lot on that part just because it gets a little bit crazy. And then the third one, the biggest one that everybody likes to ask about, not that it's a common question that we can get to, is what is the likelihood of exoplanets being habitable as we can think of? How common is it that planets can potentially support life? How unique is Earth? And then, of course, the ultimate question, which is the topic of any astrobiology talk: are we alone, and how can we tell? Okay, I don't want to do complete spoilers for the end of it, but the answer to that final question is ... to be continued, because we honestly don't know yet. Let's see if PowerPoint's going to behave. Okay, types of exoplanets. Okay, according to the Unified Astronomy Thesaurus, which honestly until a week ago I didn't realize existed, but it is a publication of the Planetary Society, there are 15 official types of exoplanets, although often those types can be cross-referenced, so it's possible for one exoplanet to fit in 3 different categories. So when NASA talks about exoplanets, they talk about basically 5 different types. We have Neptune-like planets, which are kind of intermediately sized, not as big as Jupiter, but not as small as Earth. And they're typically more ice giants, so they're frozen, like methane and other gases that are typically referred to in astronomy circles as ices. You have gas giants like Jupiter's, and those are Jupiter-like planets in our solar system and Jupiter-like planets in other solar systems, and what we call hot Jupiters, which are the Jupiters that are essentially Jupiter-sized planets inside the orbit of Mercury or Venus. We have super Earths, which are planets that are Earth-like, but more massive and slightly larger. Typically, they have rocky cores, and they look similar in composition to Earth, but might be 2 to 3 Earth radii large, so they might be somewhere between 6 and 10 times the volume of the planet, maybe 5 times the surface area, and as I said, so slightly larger, and as a result, slightly more massive. We have terrestrial planets, which are rocky planets similar to Venus, Earth, and Mars, and some of those are down to Earth size at this point. And then we have the 5th category, which is anything else that could end up being an exoplanet that doesn't fit a category that we've previously thought of based on things we've seen before. As always with science, it's always best to always have an unknown category, because there will be things that come up that you didn't realize you didn't know about yet. So the first thing we always acknowledge in science is the fact that there are things that we don't know. And particularly when dealing with astronomy or astrophysics, there are a lot of things you don't know, because we haven't had the technology or the ability to look for it yet. Okay, so why do we care about exoplanets? And And this is actually a very relatively new field. This is 2020, although I swear 2020 feels like it's taken 7 years already, but it's still, to the best of my knowledge, still only October of 2020. And the first hot Jupiter observations that were confirmed occurred back in 1995. So 25 years ago exactly, were about the first time that there were published results of finding an exoplanet near, and we'll talk about 51 Peg in a minute. It's in one of those situations where it really wants its spotlight and it's not there yet. Was originally confirmed in 1995. Didier Queloz and Michel Mayor at an observatory in France, also confirmed by Jeff Marcy and collaborators at the University of Arizona, found the hot Jupiter known as 51 Peg B. And this very discovery was what Didier Queloz and Michel Mayor were given the Nobel Prize in Physics for last year. So this very discussion of exoplanets was the Nobel Prize winning discussion of last year in 2019. They were awarded a Nobel Prize as a result of their initial findings of exoplanets and then their continued work in the field since then. So we'll talk about the first planet that we saw, or that was confirmed. This is a planet, we call it 51 Peg B. It's 51 Pegasi B. It's the 51st star in the constellation of Pegasus, and B is just the planet. So we have the star and then the planet is B. You'll see a lot of these planet names, exoplanet names have really strange nomenclature. It's because we don't actually have names for them yet. 51 Peg B, we actually have sort of given it a name, Bellerophon, but nobody actually uses it. We just call it 51 Peg B. And one of the biggest ways that we can find it now and actually learn more about its atmosphere is looking at spectra as it transits its planet. And we'll talk more about what transits mean later on. But one of the key things to doing exoplanet research is we would like to be able to identify what is in the atmosphere of these planets. That has direct ties to habitability. It also has direct ties to what kinds of basically elemental compounds and what kinds of chemical makeup do those atmospheres have in terms of what can we learn about what may be available at those planets. I know we didn't say this before, but I'll pause here for a minute and suggest that should any questions arise, I am a professional filibusterer. I teach at the college full time. So if any questions arise, there is a button on your Zoom that will allow you to raise your hand. Drea, I'm sure you'll keep an eye out if there are hands for questions. Please feel free to stop me so I can answer questions. It might be more fun to do that as we go rather than wait till the very end, because it's possible that questions could get lost midway through. So, okay, so how do we find exoplanets? And we find exoplanets by a number of different things. We find exoplanets through measurements of radial velocity. And by measurements of radial velocity changes, essentially what we found, and this was the first way we found them back in '95, was we would observe a star for an extended period of time. And as we got spectra from that star, we would detect a wobble in that star that would cause the light to either redshift or blue shift as it went away from us or towards us. And part of that wobble is due to the gravitational impact of there being an unseen planet there. So the fact that we were seeing the spectra of known lines that we knew about from certain elements shifting back and forth red to blue, albeit slightly, we could detect that there was an unseen gravitational force that was actually causing that acceleration that was causing it to redshift or blue shift, either toward or away from us, depending on which way the star was rotating at the time. So we look for these wobbles by looking at the spectra and looking at the Doppler shift. The Doppler shift basically tells us that if light is moving towards us, it will shift toward the blue. It'll become higher energy, it'll become higher frequency, lower wavelength, and shift toward the blue. And as it's going away from us, it'll shift to the red, which makes it longer wavelength, less energy, and typically shifted to the red indicates colder temperature-wise, but we're not as worried about the temperature rating as much in this case as we are just looking at how the radial velocity would vary. So we would pick up these wobbles in certain planets. Now I had another slide for this, but I'm going to skip it because I actually had it. I was in mid-thought, and then I decided I wouldn't go into complete detail on it, but we'll talk about it a little bit before we go there. The radial velocity measurements had kind of there's a selection effect there. With radial velocity measurements at the resolution that we had, it's harder to pick up smaller planets. So there was a bit of a selection effect with the radial velocity measurements, and we'll see that in a couple of the later graphs, that in the early days of exoplanet searches, we found a lot of Jupiter-sized planets. Some very hot because they're really close to their parent stars, some not as hot because they're further out, but we were kind of limited to Jupiter-sized planets, and then sort of to the lower extreme, we could get to like Neptune-sized planets or Uranus-sized planets, but that would be about as small as we could get. And then we started looking at other options. And one of the biggest options that we use now, and what we'll focus a lot of this particular talk on, are transits. We'll talk a little bit also about gravitational microlensing, and there are a couple of cases of direct imaging. That's the one. Okay, so this is a picture of essentially, this is a Doppler method for detecting planets. As the star goes around, if we're seeing kind of an unseen planet that orbits, or not seeing the planet, but we notice the unseen planet, as the star orbits, it's going to approach us and it's going to wobble so that the light will shift to the blue. So we'll get an observation where everything will get shifted up in wavelength toward the blue end of the spectrum to smaller wavelengths. As it's going away from us, it'll shift out to the red, and we can measure essentially what that Doppler shift is and get more information about the mass and the size of the particular unseen planet that we're dealing with. This is actually a figure from the astronomy textbook I use. It's from OpenStax, which is run by Rice University, and all of the OpenStax textbooks are free as PDFs. So if astronomy is one of those topics that you're very interested in, there's a free college level textbook if you just go to openstax.org and search for the astronomy text. It's about 1,200 pages of astronomy, and it's all updated, and they update it about once a year. And as I said, it's free as a PDF, or if you want to get the hard copy, it's like 30 or 40 bucks. But it's a very good astronomy text, and I use it for my classes. We'll skip through the one that. So what do these things look like? I told you 51 Peg was what's called a hot Jupiter. This is an artist painting by an artist by the name of Greg Bacon. And despite what my assistant will likely think, Wade, no, I didn't pick this picture because of the artist's last name. But it is a simulation of essentially what a hot Jupiter would look like. We think of a Jupiter as a giant gas planet similar to Jupiter in our own solar system, but then we have but in this case, instead of being further out past the asteroid belt like Jupiter is in our system, this is a Jupiter that is now sitting essentially inside the orbit of Mercury. So it's essentially right next door to the planet star, or to the host star. Jupiter-type planets are usually detected through the Doppler method, and we're not exactly sure what the conditions on those planets are like. I'm guessing, given being close to sun-like stars or even hotter stars than that, conditions are I'm going to go out on a limb and say conditions are fairly miserable. But in terms of the specifics, in terms of what they would look like, we're not entirely sure because we don't really have the resolution to be able to detect temperatures at this point. So one of the methods that we use is we use transits, and this is the one that is proven most effective. And a transit occurs when a planet, or when planets, you can actually have multiples cross at the same time. That would be extremely rare. Usually you only get one planet across at a time, because to have multiples cross, you'd have to have things in very precise sort of locked orbits. So typically you'll only have one planet transit at a time, but you'll have a planet that crosses in front of a star, and because it crosses in front of a star, it's basically a mini eclipse. It doesn't block off enough of the star that it cuts all the light down, but it blocks enough of the star that you can detect it. If you're looking at essentially a brightness light curve, you can detect that dip. You can detect a dip in brightness, and that will give you an idea that gives you some information about the size of the planet, and the amount of time it takes to cross gives you an idea of where the planet is in terms of its orbit. And we know these types of things exist because we see it in our own solar system. Looking from Earth, we occasionally get to see transits of Mercury or transits of Venus, because as we look at the sun, sometimes because of the way the orbital mechanics work, Mercury will pass in front of the sun, and we'll see it go across the solar surface in at least for a period of a couple of hours. The last one of those, if I remember correctly, the transit of Mercury was Veterans Day of last year. So there was one November 11th of last year. They don't happen that often, but they happen. I don't remember the exact duration of time, but it's typically like a decade or so between either a transit of Mercury or a transit of Venus. We can see transits of Mercury. We can see transits of Venus. I went backwards. I went the wrong way. So if they happen in our solar system, it would be it wouldn't necessarily be the best scientific approach to think that if it can happen here, it would be kind of odd if it only happened here and didn't happen anywhere else. So one of the ways we've gone about finding planets is basically staring at other stars and waiting to detect some of these drops. And we have 2 satellites that do that very well, or did. TESS is still going. But before TESS, we had Kepler, which was basically a planet hunting mission that stared off into a very small quadrant of space and just observed the stars in that particular field for years and would wait for signals that indicated these drops in intensity of known targets. And this would indicate that there was a transiting exoplanet.
Dr. Coyner, we have a raised hand.
Okay, we have a question. Yes, go ahead.
Are there computer models of possible planet orbital configurations to help identify how many planets there could be and what angles they orbit at? Have we been able to model our solar system properly?
Let's see. Our solar system, yes, there are computer models for it, although they keep adapting because we keep finding space debris that we didn't realize was there. Because one of the things you'll find out as you study more about space is very, very big. And given that space is extremely large, there are any number of things that there is only a small portion of space that we can actually have observational eyes on at any given time. That's why we find things like, did anybody in the audience, other than the few people that I roped into going outside, I hope you guys got a chance to see Comet Neowise when it was out back in July or back in late July when we had the comet that went by. That comet wasn't discovered until a satellite found it like in March, and then we watched it in July. So there's a lot of new things that get found in astronomy, even though we have an idea of kind of how our solar system works, but we find stuff pretty much every year that we didn't realize was there, whether it be additional asteroids, whether it be additional comets that we weren't aware of, whether it be new moons of planets that we know had moons, but a lot of those turn out to be captured asteroids. And Jupiter's very good at capturing asteroids, and we're very grateful for that, because if it didn't, a lot of those asteroids would come crashing into us, and I don't think we're quite prepared for that. Although with the way 2020 is going, I think the December space on my 2020 bingo card is cataclysmic asteroid collision, but I'm still hoping I don't have to use that one. So before I go into TESS, so as we were talking about transiting planets, about 3/4 of the exoplanets that we discover through transit observations. It's the most effective technique we have with current technology. And we conveniently have a satellite that started after Kepler that was the named TESS, which is conveniently named the Transiting Exoplanet Survey Satellite, which by its name basically means it's going to stare at things and look for transiting exoplanets and take a survey of all the ones it can find. And so this is a little bit on TESS, and I borrow this from, as I said, Dr. Joshua Slider from NASA Goddard. He's working with the TESS team, which is actually headquartered at MIT. And TESS itself, we're looking at like space-based transits, which are easier to do and kind of important to go through. And so we have space-based transit. If we look from space, we don't have to worry about our own atmosphere getting in the way. And for any of you that have tried to do any sort of astronomy from the lovely coast of Oregon, I love living here, but it's not exactly the most friendly place to actually do observational astronomy, given the fact that the marine layer likes to show up at the absolute least appropriate time for most things. And about half the year it decides to rain, which makes it a little difficult to actually look for fun things from the ground. But if we're doing this from space, whatever happens in our atmosphere stays in our atmosphere and doesn't actually affect us. So Kepler was kind of the first mission to take advantage of this. And we were using a satellite in space, and we just told it, hey, stare at the constellation of Cygnus the Swan and see what you can come up with. And it had a nice field of view, which was this bubble thing. I'll actually I'll make things bigger because I can. And so the Kepler field of view is kind of this red box. It's a little bigger, but most of the stuff comes in that red box. Move the control box down. So if you're looking at sort of the Kepler field of view, this is the only part of the, we just said space is big, and well, Kepler is looking basically in this cube right here. By comparison, we'll see how small that is in a later slide. So I'll clear off my box. Freeze things up. Technical difficulties. One moment, please, while I figure out why PowerPoint doesn't like me. I tried to get too creative with Zoom and paid the price.
You got too close to the sun, didn't you?
I got too close to the sun for the purposes of technology. I should always be aware that these things aren't going to happen. Okay, so Kepler started doing this in 2009. And over the course of about 8.5 years that it was actually working, well, it was working for longer than that, but for the bulk of the mission was about 4 years of the mission from 2009 to 2013. It stared at 150,000 stars every 30 minutes for about 4 years. And we wanted to find, essentially we wanted to measure the frequency of finding Earth-like planets around sun-like stars. And Dr. Slider says that Kepler was a statistical mission. We were going to try to find as many things as we could, and then we were going to figure out kind of proportions of, okay, we found this many planets, how many of them are Earth-like? And we went and looked through Kepler data. We're still looking at Kepler data. This is a little better picture of what the field of view looks like. This is from the astronomy text that I use in class. It's the same little box. And Kepler's going to measure things in terms of transits, where, like, say, Kepler 4b, it's a smaller planet, so you get a much smaller drop-off. You get an orbital period of about 3.2 days, because you get the transit that lasts a little less, or that is fairly short. You've got Kepler 5b, which is one of the earlier ones. It's a much larger planet because you get a much larger drop-off, and it ends up having an orbital period of about 3.5 days. And Kepler 6b is kind of in the, it's a larger planet because they get a much larger drop-off, but this one has a planet of, or has an orbital period of about 3.2 days. So these are some of, like, the hot Jupiter ones that we were talking about before. Much larger planets, very fast orbits, meaning they have to be really close to their star. And because they're causing this much of a drop-off during their transit, we know that they have to be fairly large. And so since we had 4 years of data, this gave us extremely good precision, plus we had a long baseline so we could look at what stars looked like when they weren't experiencing transits. It made it very easy to detect transits if we had a lot of observations where there was nothing going on. It's always good to have a control group. So yeah, we'll stare at the same star multiple times, and then when you look at something multiple times over the course of several years, and it always looks the same, and then all of a sudden doesn't, you actually start to notice when things don't look right. And that's essentially what happens with the transit measurements that we do with Kepler. And so this is the December of 2017. This is the type of orbital periods, and we have anything from orbital periods of slightly less than a day or significantly less than a day to orbital periods of 1 day, 10 days, 100 days, out to 1,000 days. So we're looking at anything from, say, a couple of hours out to say 10 days, out to say 100 days. When we get out to 300 days or thereabouts, we're starting to talk about an Earth, or 365 days would be an Earth year. Mars is about 1.88 years. So when you're looking at about 600 days or about 700 days, you're looking at about Mars. And Venus is about 243. So out here, you're looking about, so Venus, Earth, and Mars are all going to be out in this area, or Venus, Earth, and Mars-like orbits are going to be out in this area of the graph. Some of the ones that are less than a day, you can imagine how quick that is by planetary systems. And Kepler was responsible for a giant boom in the total amount of planets. And this is in December of 2017, so this is almost 3 years ago now. And at that point, we had a total confirmed exoplanets of 3,567, and of which Kepler was responsible for over 70% of those at 2,525. I also want you to notice something about the graph itself. Kepler has a propensity to find things that are, in terms of the star size compared to, say, Earth radii, we're looking at a large band of planets that are between 1 and 4 Earth radii. So these are the Earth-like terrestrial planets. These are the super Earths we talk about, and these are like the Neptune-like planets. You'll notice some of the earlier ones that are before Kepler, and then others with ground-based observations. A lot of the ground-based observations were kind of limited to we're still limited to finding only planets that are 10 to 20 times the radius of Earth, whereas Kepler and TESS later on. Important to note that this is of December 2017, so none of the TESS data is in here yet because TESS didn't launch until April of 2018. But this is Kepler versus essentially ground-based and Hubble Space Telescope observations. And you can see that the Kepler data has many of the smaller planets, whereas the ground-based observations are sort of limited to sort of the upper ranges of Neptune size and above planets. So we're finding all kinds of newer and smaller planets using the precision that Kepler provides. And so this is sort of a finalized thing. This is actually as of like the 1st of October. And we can see that the Kepler planet candidates, they're all kind of down here. So all the pink dots are between like 15 and between like 20 times the radius of the Earth all the way down to 1 or less. My computer is haunted sometimes and decides to move. And all the green ones that you're seeing are confirmed planets just from the Kepler mission. And so we know that Kepler is having a selection effect, which helps us in that we're seeing a lot more Earth-like planets. We're seeing a lot more super Earths and sort of Neptune-sized planets as compared to always having to look for these hot Jupiters. So what did we learn from Kepler? Well, if we look at essentially planet size relative to the Earth and sort of the fraction of stars with at least one planet, if we look at sort of Earth-sized planets, we find those about 15 to 20% of the time. So about 15 to 20% of stars will have at least one Earth-sized planet. Well, I don't know about you, but I know that there are hundreds of millions, if not billions, of stars within our galaxy, and there are hundreds of billions of galaxies other than our galaxy. And if say 15 to 20% of stars within each one of those galaxies has the potential of having an Earth-like planet, that number becomes too high for me to calculate. I mean, I can bust out a calculator. We can calculate as many as we want, and that number and that potential number, if I look at things from an astronomical perspective, means that there are a whole lot of little Earths like us that are out there amongst other stars. We just have to find them all. And that is not to say anything about astrobiology right now as much as it is to say, hey, we're not as uncommon and as special as we thought we were. Because planets like us form fairly easily according to the survey that, and remember, Kepler was just taking a small sample size of a small patch of the night sky that wasn't really all that very big, and we're still seeing these. In terms of super Earths, we're looking at, say, planets that are 1 1/4 to twice the radius of Earth. We get about 20% of planets that have these size planets. Mini Neptunes, things that are 2 to 4 times the radius of Earth. About 20% of planetary systems have those. If we look at large Neptunes, about 4 to 6 radii, we only see about 2% of the planets that we find are in that range, and about 2% of the planets that we find are gas giants, which are bigger than 6 Earth radii. So these are the Jupiters. So the ones that we were finding early with the Doppler method, which we were predominantly finding these types of Neptune size and gas giant planets, they're not nearly as prevalent according to Kepler's survey as any of the smaller planets that the smaller types of planets that we're looking for. And this is again as of 2013, so these numbers did change a little bit, but the relative proportions are about the same. So planets are common, and most stars actually have at least one, which is a completely different far cry from the things that I was taught as an astronomy student years ago. I'll say about 3 decades ago, when I was in school taking astronomy classes and learning about these, we didn't really at that point talk about there being any planets outside of our own solar system, and now we're finding out that there are so many and they are so prevalent that statistically speaking, it is more likely for a star to have a planetary system than not. Super Earths and mini Neptune things are the most frequent ones. And Earth-sized planets in habitable zones because we always want to know about that, because we'd like to find planets that are like ours, that have similar conditions to ours, that aren't too far away, so that in case we do need to get off this rock before too long, we could actually do it. We're not anywhere close to that point yet, but we always like to know that. And part of the things is we like to know, if to answer the question, are we alone in the universe? How easy is it to create a system like ours where we have a planet that's Earth-like in size and composition and exists in sort of the same position relative to its star, to where it could be in the habitable zone? And how do we manage to make, and if those are common, then whether or not life forms on any of those becomes more of a question of how did the rest of circumstances play out, more so than getting the planet to exist is kind of a first step to that. If the planet doesn't exist and isn't in the habitable zone, then we can sort of stop the, okay, where does the chain of astrobiological development go? If I don't have a planet, I don't get to even start to talk about it. And then if I have a planet and it's not in the habitable zone, then everything gets irradiated before then. But once I'm in the habitable zone, then you start asking questions about, okay, what is there? Is there a magnetic field to protect us from the radiation? Is there an atmosphere to help essentially create organic compounds, and also help those of us that are any kind of human-like, or any of the life that we know of? Would there be enough of an atmosphere to help them breathe? Assuming that, and this is one of the big assumptions that we have to make and acknowledge that we're making when we're talking about astrobiology, is a lot of the things that we look for in terms of astrobiological signatures, we look for signatures that look like life that we would actually recognize. Which is, of course, setting up a selection effect to, we're making the assumption that we actually know what life in other planets and in other places is going to look like. So this is an example, and I'll bring up a picture of this later, but one of the planets, or one of the planetary systems that Kepler found was an M dwarf. The habitable zones of M dwarfs are typically closer in. They're about 1/10 of the weight of an Earth orbit, so about 1/10 of an AU. And an M dwarf is typically a very stable star. By comparison to other stars, M dwarfs are extremely stable. Those of you that know me personally, you'll get this reference and you understand it. Those of you that don't, a little bit of background. I am not only a scientist, I'm a diehard comic nerd. So when I make this reference, this comes from Marvel Comics, but essentially the M dwarfs are the watchers of the universe. And if you've read Marvel Comics, you're aware the watchers are basically eternal beings that can basically just look on and observe what happens everywhere else, and they're not supposed to intervene, and they just basically stand there and watch things happen. They can't die, so they just observe what goes around, and then they record it for the purpose of history's sake. They're universal librarians, except they don't get to go home, and except they don't really get to go home, and they never actually get to sleep or die. So as a result, they get to watch everything. M dwarfs are essentially the same way. Whereas hotter, larger stars like O-type stars and B-type stars will burn out over the course of tens to hundreds of thousands of years. And like the star Betelgeuse is actually a red giant that's only about only a couple of tens of thousand years old, and we're already anticipating that sometime in the near future, it's probably going to reach its last legs and go supernova. Whereas that is the case on one end of the spectrum, you have the M dwarfs that basically can have mean sequence lifetimes of 1 trillion years. Now, the observable universe, as far as we can tell, is only 14 billion years old. So the M dwarfs are basically still babies within their evolution. So they will still continue to be there for at least the foreseeable future. We have never seen an M dwarf die because they're not really hot enough to do anything too terribly explosive. And so if we find planets around M dwarfs, we know that these, we have a feeling that these systems are slightly more stable. Now, they're a little bit interesting in that they're not as warm as, say, a G star, which is a sun-like star, so there's not as much energy in there. And that's part of the reason why the habitable zones are much closer, is because you only have so much energy coming out of the star, so you actually have to be closer to it for things to warm up enough to have some of the necessary organic compounds for life. Okay, I'm going to pause for a minute to take a breath. Dre, do we have any questions? And can I get a time update so that I know I'm not filibustering myself out of commission here?
We do not have any questions, and it is 7:24.
Okay, so I'm actually not doing too bad as far as time goes, but it's kind of hard for me to tell when I do these things. Okay, so when we look at M dwarfs, you can have a really close-in habitable zone, and if we look at the Kepler 186 system, there's actually 5 planets in there. There's B, C, D, E, and F. But B, C, D, and E are all very close in, and they're actually inside the habitable zone, so they're closer to Mercury by comparison. So B, C, D, and E for Kepler 186 basically would fit in, by comparison to a sun-like star, would be between like Mercury and Venus for the sun. However, Kepler 186f, which is the one we like to point out as the one closest to Earth, is roughly Earth size. It's about 1.25 Earth radii, and it's in the habitable zone of its star. It's out here in sort of the light green, and the light green color is something that NASA typically uses to identify the habitable zones, because well, we usually associate green with being go. So this is essentially an area that is potentially go for life. And this is one of the planets that Kepler has identified, and we found a number of other planets similar to Kepler 186f that are in the habitable zone around stars that are M dwarf stars, or that are sun-like stars that are G stars, that we think could be in habitable zones, and we just need to be able to do some more analysis of the spectra and the chemical composition to figure out what exactly is there. More on that later, because there's always more missions to come. Scientific principle number 1, never design yourself out of a job, and also always have another mission as a backup plan for when this one's mission ends. Always use the information you get from the previous mission to design a follow-up mission to continue the work that you're doing.
Dr. Coyner, we have a question. Yeah. Is
okay.
it possible to tell if these have magnetic fields?
It is to an extent. And a lot of that right now is we're working on modeling for it. And I'm not going to pretend to be an expert on that, but I will tell you, I will tell you that in March, we had a guest speaker at Southwestern by the name of Dr. David Alexander, who we can blame for the fact that I actually have my PhD, because he was my my PhD advisor. But he has been working with current grad students of his to sort of model the magnetosphere of other potential sun-like stars and sort of look at what criteria for a magnetic field you would need in order for an exoplanet to be habitable. And he talked to us at SWOCC about that in March. And actually, there's a link, and if I can do this, I'll put a link in the chat so that everybody can find it. If you go to if you just go to livestream.com/SWOCC and then look for let me make sure I send that to everybody. And then it should say Physics and Astronomy 1920. Or 2019-20. You'll see the archives of the Physics and Astronomy lecture series we did last academic year. And Dr. Alexander's talk is, I believe, the second one from the bottom in the archive. And you can learn more about studies in terms of the magnetic field and habitability that are ongoing at this particular moment. I am working with Dr. Alexander on a paper. He's actually got me working on a project, except right now I've been so swamped with trying to teach things online and trying to adapt all my curriculum that I haven't exactly had a whole lot of time for research, but that is something that is currently ongoing, and I'm waiting till after Thanksgiving when I actually get a month off from teaching to sit down and do a month's worth of research. But we will see how far that gets. But that should help with that one. Let's see what else is on the agenda and see if everything's going to behave. So this is TESS. TESS is actually an MIT-led. It's considered a NASA astrophysics explorer mission. It was scheduled for launch in April, and it actually did launch in April. It launched in April of 2018, April 18th. That's what the satellite looks like. It has 4 different cameras with CCD detectors. It has wide field of view, high precision. We're looking at 0.2% precision for bright stars that go to 10th magnitude. We can have 2-minute cadence for like 200,000 stars. And remember we said Kepler looked at 150,000 stars for like 30 minutes, like every 30 minutes for 4 years? Well, if we do an every 30 minutes study with TESS, instead of 150,000 stars, we can now do 20 million stars. And we're doing an all-sky survey over the course of 2 years, which should be about done in the initial phases. And we'll continue to have, it has a secondary mission that will continue to cycle through these all-sky surveys, and we'll continue to observe more. And we started in the southern ecliptic, and it's designed to detect transiting planets. So, okay, here's what we've got. The yellow swath here is the Kepler search space. It's about 3,000 light years, and it's kind of a small triangular field, because there's that square that we looked at earlier, and we've basically got this cone that we're dealing with here. Everything else in this picture is what TESS can look at. And TESS can actually also look at the Kepler range. So the entire square, or the entire rectangle of field of view here is the stuff that TESS will survey over the next 2 to 5 years, most of which it's actually already done. But as with anything with astronomy, remember most of Kepler's observations were between 2004 and 2009. And we were still processing Kepler data until 2017. So TESS has been up since it launched in April of 2018. Its first light image was August of 2018. So it's been up and it's been operational and observing things for slightly more than 2 years. But taking images at extremely high cadence of, say, 2 minutes. So if we're taking 2-minute images for 24 hours a day, every day, for 2 solid years, you can imagine there's a lot of images that still need to be processed, and there are people and there is computing power that needs to be used to process all those images. So I'm going to show you some numbers of what TESS has done so far, and it may look relatively small compared to what Kepler did, but keep in mind we're still in the early stages of processing a lot of the test results. Let's see. Okay, so here's what we've got for test results so far. Launched in April of 2018. First light was in August. Results as of September 1st, we had 2,230 targets of interest, 79 of which had been confirmed to be planets, 500 of which had been false positives, but that's just in that first swath of data. And then we had, so far we found 704 candidates with tests that were less than 4 Earth radii in size, so super Earths or smaller. And so that's from the test mission page and from the NASA Exoplanet Archive.
We just had a question come in if the test images are available online for astronomy students. From what you just said, I'm assuming yes.
The data should be. Since it is a NASA mission, I believe it falls under the NASA Open Web situation where you can actually find the data. Now, whether you can find the data in a form that makes any sense is a whole different question. But I believe you can actually find some of the data, and at least I know with the Exoplanet Archive, they update that I believe they update that once a week with what they've confirmed as planets and what new candidates are. So you can actually, so that is one thing you can check. And if you just search for NASA Exoplanet Archive, it'll take you to that page, and it updates itself. If not daily, it updates itself at least weekly. And just so that we're clear that we don't completely make this stuff up, there are some times that we get lucky enough. This is actually using ground-based, although I use ground-based extremely loosely in this case because this is observations from the Keck telescope, which is on top of Mauna Kea in Hawaii. Which means, yes, technically it's ground-based because it's on top of a 14,000-foot mountain. But if you actually I've actually had colleagues and friends of mine that have observed up there. When you're up on top of Mauna Kea, you're actually looking down at the clouds most of the time because the mountain is much higher than the cloud base is in that particular area, which is one of the reasons why there's a telescope up there. But when we observe things from Mauna Kea, in this case we sort of took this blue bubble to be about 28, you were about 20 Earth orbits out. The star is in the center and it's been blocked away by an occulting disk. And we can see 4 different planets. There's one that's sort of out here on the outskirts. There's one kind of in the middle. And then there's 2 other ones that are progressively in closer. So in this case, we were able to find, we're able to find direct observations, direct visual evidence of 4 exoplanets orbiting around a star, HR 8799. So this is another graph. This is from Hubble Space Telescope. This is from spacetoLescope.org, and we can look at exoplanets in terms of looking at the radius, the distance from the star, and the size of the planet. And within 1 million miles, you see a lot of smaller planets, you see some Earth-like stuff, you see some super Earths, and you see some hot Jupiters that are really big. But in this sort of top of the super Earths, kind of mini Neptunes and the Neptune-sized planets, you don't see any of those inside of about 9 or 10 million miles. So there's a bubble in here that would indicate that if you get too close to the star, you can't have a hot Neptune-like planet. And that would make sense because the Neptune-like planets typically result from ices and things like methane that get frozen. And if you're that close to the star, you're not going to likely have that much frozen ice to deal with. So let's talk about a little bit of some intriguing exoplanets. The favorite one that my students like to bring up is TRAPPIST-1. And TRAPPIST-1 is a complicated system that has 7 planets that are all believed to be inside of the habitable zone. And they all have different sizes and shapes, and they all look fairly odd, but there are 7 planets inside the habitable zone of the star, and we believe at least 3 to 4 of them are roughly Earth size. As far as looking at compositions and things, we still need to do more spectral analysis, and that's what happens when James Webb Space Telescope goes up next year. The other intriguing one, and yeah, I used it as my background for this one because it's the cool one to think about, Proxima Centauri, which is the nearest star to us that isn't the sun. It's about 4.1 light years away. It is the nearest star other than our sun, and it even has a planetary system that has at least 2 confirmed planets. And it, like we mentioned before, is similar to what we mentioned with Kepler 186. This is a M5.5 dwarf, so this is a much cooler, much smaller star that has a much longer life expectancy than the sun does.
We have a question. Will the new James Webb Telescope be able to analyze exoplanet atmospheres to detect byproducts of biological life? Also a comment. Thank you. Excellent presentation.
The belief is that James Webb, when it finally does get launched, should have the capability to do more of those atmospheric composition spectra, and we should be able to start looking for biological compounds. At least that's what the mission, one of the main missions of James Webb Space Telescope is intended to do. Now, I am always a little bit hesitant when I talk about James Webb because I was a postdoc at NASA Goddard for 3 years between 2008 and 2011. And when I was at NASA Goddard, one of the main missions that they were talking about at the time that was occupying like 2 buildings worth of the science team at NASA Goddard at that particular point was getting the initial phases of James Webb Space Telescope ready to go. That was 9 to 12 years ago. And James Webb Space Telescope is still sitting in a hangar somewhere waiting for an official launch date, which last I checked was supposed to be sometime in 2021, but last I looked was a while ago, before we all went into hyper isolation mode for 6 months, including most of the space program. So as for what that timeline looks like, I'm still hopeful that James Webb will launch in 2021. Hopefully they won't push it back too much further, because it's been on the list of things to get launched for years now, but because of the cost of it, among other things, it tends to become a little bit of a scientific political football. So it's whenever it's convenient to launch James Webb and Congress isn't complaining about how much it cost, then they'll actually launch it, which hopefully will be next year.
We also have a question, is there room to improve on modern telescopes to see exoplanets better than the James Webb one?
The answer to that is always yes, but exactly how to improve it and where to specifically start, a lot of that's going to depend on, we based what we set up James Webb to do based on what Hubble was capable of doing. And then I think what we'll find out is when we have, between Kepler and TESS and JWST, I think those 3 missions will set out additional follow-up missions that will continue to refine our ability to detect exoplanets as we go. But depending on the results of those previous missions will sort of guide the engineering for what the follow-up missions look like. And those discussions are actually already ongoing. And I've got one other one that's a really interesting one. And this is one of TESS's first Earth-sized planets that we found in a habitable zone. I said these all come with really weird names. This is TOI 700D, target of interest number 700, planet D. Luckily, my friends at Goddard put this video together. It's about 3 minutes long. So you get to listen to them talk more entertainingly for about 3 minutes while I catch my breath for a minute.
NASA's TESS mission has found its first Earth-sized world in its star's habitable zone. This means the planet, called TOI 700D, has the potential for liquid water on its surface. TESS stares at patches of sky for long stretches, recording light from thousands of stars. Some of these stars have planets that cross or transit in front of them. TESS sees these events as tiny, regular dimmings of the host stars. One star where TESS saw transits is TOI 700. It's a red dwarf about 40% the mass and size of our Sun and roughly half its temperature. One set of transits announced the presence of a planet close to the star, called TOI 700b. Another set revealed a second planet named TOI 700c a little farther out. The deeper, shorter transit means the planet is larger than the first, and the plane of its orbit is slightly tipped. A final set of transits showed TOI 700d orbiting even farther out. TESS observed the system for nearly 11 months and saw each planet transit multiple times. Scientists determined that the inner and outer planets are almost Earth-size and may be rocky. The middle world is more than twice as large and most likely made of gas. All 3 may be tidally locked, rotating just once each orbit, so the same side always faces the star. But most importantly, TOI 700d is within the star's habitable zone. Scientists wanted independent confirmation of TOI 700d, so they monitored its star with NASA's Spitzer Space Telescope. Spitzer saw a clear transit from the outer planet, affirming its existence and improving scientists' certainty of the planet's size. TOI 700d is one of only a few Earth-sized planets found in potential habitable zones. Others include discoveries by Kepler and several planets in the TRAPPIST-1 system. Because TOI 700 is bright and nearby, the planets are good candidates for precise mass measurements by ground-based telescopes. Future missions may also tell us if the worlds have atmospheres, but scientists need to know what kinds of signals to look for. Researchers at NASA's Goddard Space Flight Center created models of the planet to explore its potential conditions. One version is a water-covered world with an atmosphere similar to early Mars, but denser. Another looks like a completely dry version of today's Earth. Both models have vastly different surface temperatures. Light passing through their atmospheres creates distinct signals because different molecules are present. By simulating these data now, scientists can make predictions for real future observations and narrow the range of TOI 700D's possible conditions. We still have much to learn about the TOI 700 system, but thanks to Tess, Spitzer, and the work of many scientists, we're beginning to form a picture of its exciting new worlds.
And we appreciate our dear friends at NASA for putting that video together. And the last one I put in just sort of as an intriguing exoplanet is we talked a little bit about Kepler 186f. And the artistic representation is basically one that's slightly larger than Earth because it's about 1 1/5 the size of Earth from a radius perspective. And it's roughly Earth-like. We don't know that it has water. This was an artistic representation. When we look at the other artistic representation from the other aspect, it's basically, it looks brown, but we don't really know because we don't have the types of cameras to be able to determine exactly what these planets look like as far out as they are. So as for what the planets actually look like, a lot of that is left up to our own interpretation.
We do have another question, which is to say, with the increase of hundreds and thousands of low orbit communication satellites, have Earth-based observations become more difficult?
They have become more difficult in certain aspects. There are places on Earth. A lot of the standard locations like the Keck Observatory, like Atacama, which is in Chile, and some of the great European observatories that have been doing this for a very long time, many of those were taken into account when coming up with the orbits for those low Earth orbit satellites, so that they didn't necessarily cross in front of, or they didn't cross in front of those particular telescope sites very often. Now, with Starlink and the number of things that are going up now, I don't necessarily know how drastically that's going to affect. It will have some effect. I'm hoping it's not going to be as drastic as I fear. I know some of my observational astronomy colleagues are livid about the number of satellites that are being put up now, because it's going to make it extremely difficult to do. It's going to make it extremely difficult in some cases to do long exposure sort of astrophotography and ground-based observations over a long period of time without at least some degree of knowing how to background subtract out those satellites, and we don't have that information yet. My hope is that the effects will be minimized, because there has been a groundswell of activity from the astronomical community to sort of raise these questions to the satellite companies in hopes that they will at least take some of the astronomical information and just the preservation of our night sky into consideration. But many of these being corporate decisions, we don't necessarily know how much science will necessarily play in. We are hopeful, but at this point, it's still anybody's guess. Which is why most of this talk I've focused on a lot of the space-based observations, because I think that's where a lot of our best findings are going to come for now. because they're much, the ability to get precise measurements and consistent measurements is greatly increased by having these space-based telescopes as opposed to being ground-based telescopes where we're dealing with weather, dealing with satellites passing over, and dealing with other potential complications.
Dr. Coyner, I hate to break in, but we are now at about 5 to 8, and unfortunately, I actually have another meeting after this, and as your host, need to ask you to wrap up.
That's okay. I only have one slide left because this is a question about, we did have a question about astrobiology and the sort of in the general setup of this talk. This is why we needed to find all these exoplanets, and then the astrobiology questions come in as we find planets in the habitable zones. What are their atmospheric compositions? That's where James Webb comes in. What are the magnetic field constraints? We talked about Dr. Alexander's lecture from March. Are we looking for organic compounds in terms of traditional life? So things like carbon dioxide, oxygen, nitrogen. Are we looking for things like that? Are we looking for extremophiles that exist in things like life that exist in lava vents, that exist on sulfur, that exist on nitrogen, or is completely based on carbon dioxide? And I'll use that to tie in for about 20 seconds into our next talk, which will be November 12th. It'll be hosted by SWOCC via a live stream link similar to the one that I sent out earlier. That's on the Europa Clipper mission. That talk will actually be given by Dr. Tracy Becker of Southwest Research Institute in San Antonio. She's actually on the science team for the Europa Clipper mission, and she'll be providing some of their data and analysis and what they hope to achieve by sending a probe to Europa and essentially drilling under the surface to explore the saltwater ocean below the surface of Europa. So we hope that you can attend that one on November 12th. I will be sending out flyers and a press release in the next couple of days to get that information out. But we hope that those of you that have managed to stick around for part 1 and part 2 of our series will be able to join us for part 3, where we'll have an opportunity to discuss more about Europa and about other possible sources of life other than just exoplanets, but not only exoplanets, but cold moons in our own solar system. And as one last plug, I suggest everyone should go to our Facebook page, which is facebook.com/SOCC for our physics and engineering department at SWOCC. We have a number of programs and a number of student opportunities, which are always ongoing. You can see some of the progress of student research. You can learn more about talks that we're bringing in and any number of other activities. My department collaborator and best friend, Crystal Hopper, does a great job of updating our social media, and you'll see posts from me about projects that the students are doing. If you want to help us out, you can reach out to the SWOCC Foundation, and if you want to help with funding of projects, or you want to make donations to help keep these discussions going on, or the overall lecture series, or some of the student research projects, you can always reach out to the SWOCC Foundation, and they are more than happy to collect charitable donations that can go to helping students learn physics and astronomy. And with all my plugs out of the way, and I know it's time to go home, I will take a breath if we have 1 or 2 more questions, or Drea, if you need us all to go, we can.
I have been asked, I have transferred the hosting over to you. I will stop recording because I do need to go. But
understandable.
So much, really appreciate this, and looking forward to part 3 so we can see about what will happen if we let the murder hornets out that are under the surface on Europa. That's my December bingo card slice. Thank you so much for your time. Please,
All
everyone,
right.
enjoy. I'm so glad to have you here. Take care.
All right. I did see the one last question, and I will take care of that one. What about removing of space debris? I think there is some discussion about how to do that, but it's more a question of how to do that safely. Because the few times in the last few years we've had satellites come down, or we've had satellites that we know have been able to bring down, we haven't necessarily known exactly how much we haven't known exactly where they were going to come down until they splashed. So it's more of a question of how do we get rid of the space debris without having it crash into civilization. Let's see. I think that's all the questions. I feel obligated. I should at least acknowledge my my favorite assistant, my little brother Wade, who stuck through this, and this was not extra credit for his science class. So he actually did this of his own volition, but he's always here to sort of help and make sure that the talk goes smoothly. So it wouldn't be possible without Wade being here. Thank you all for coming. And if there's any more questions, I'll gladly take one or two, or if there aren't any more, I will go ahead and have you guys enjoy the rest of your evening.